All right. Now, what is damping? Okay, what is damping? What system experiences damping? At this point, we have two. One, oscillation. The other one, waves. We have an oscillating system. We have a wave system. All right? Damping applies to which? Now, damping is a significant phenomenon for oscillating system, but not for a wave system. For a wave system, at your level, we can take it as a wave system. The damping process is insignificant and can be ignored, which is true. All right? Because wave, when they move through a medium, the energy of the wave is more of dissipation. That means it's dissipated. It is transferred to the medium rather than lost due to damping. Rather than lost due to the damping. Therefore, damping will not, at your level, will not be related to waves. It's related only to the oscillating system. So that perspective, we have made it clear. So damping involves oscillating system. So I'm going to take an oscillating system. So let's say this is an oscillating system. All right. So this is the system I'm taking is a spring, which has a spring with a load at the end. This is my oscillating system. So in order for me to cause this system to oscillate, what must I do? What must I do in order to cause this system to oscillate? I just went through with you. You have to cause a displacement. You either displace it down, release, or push it up, release. You have to cause a displacement in order to cause it to oscillate. So let's say we stretch, release, and it starts oscillating. All right. Now let us use a little bit of imagination. So because why? This is what we call our everyday life experiences. You have seen a cradle which is being operated by a spring, or even you have done it in any other situation. You have come across a spring which is having a load at the end and oscillating. You would have come. Now, will it oscillate forever? Okay. Okay. In a way, you can look at the swing in a playground. A swing in a playground, although the swing in a playground, it oscillates more like a pendulum, more like a pendulum system. So if you were to take the swing, displace, let go, it starts swinging. Will it go on forever swinging? No, it will stop. So a swing, such as a system of a pendulum, a spring, all right, which is vertical oscillation, all comes under one banner, under one concept called oscillation. They all will follow and obey certain laws which are very similar to that. So when you learn this system, you can apply this to a pendulum system. You can apply this to any oscillating system. So read my words carefully. I said any oscillating system, you can apply. All right? Okay. So my question back to that. Will this system oscillate forever? The answer is no. After some time, it will stop. And that is what we're going to explore. Why does it stop? So let us analyze. Why does an oscillating system stop? Go for the main idea. What's the main idea? So reverse order thinking. Ask the other way around. Why does the system oscillate in the first place? You should have questioned that. The system oscillated because you displaced. So I always told you, in order to cause any system to oscillate, you must cause a displacement. So what is it am I doing? Why is it necessary I must displace? Why? Why must I do that? So what am I doing? By me displacing, I'm putting energy. How? The spring is stretched. So when the spring is stretched, energy is supplied into the spring. With that energy, the spring causes the oscillation. So energy is needed for oscillation. So if an oscillating system stops, it is because that energy that you supplied eventually was lost. So the system stopped because it lost energy. So that means as the system is oscillating, little by little or gradually energy is lost until finally all the energy is lost and the system comes to a stop. Can you follow? This is what we call damping. Damping is a process undergone by any oscillating system, which an oscillating system experiences. It's a phenomenon. which an oscillating system experiences, whereby that oscillating system gradually loses its energy and eventually comes to a stop when it has no more energy. That process where the energy is lost, the process where an oscillating system loses energy, is called damping. Okay, damping is the process whereby an oscillating system, not a wave, you have it in wave, as I said, but as far as you are concerned, it is insignificant. Okay, so the damping is a process, a phenomenon whereby an oscillating system loses energy. All right, now let's go into more detailed thinking. Why? Why does an oscillating system lose energy? Why? Okay, let's again take a simple scenario. Okay, you are asked to do work. Let's say you're asked to mop the floor. You're asked to mop the floor. Okay, so very energetically you pick up the mop and you start mopping. After 2 hours, 3 hours of mopping, eventually what will happen to you? You'll become tired and you'll stop. But how was the initial state? You're full of energy. What's the final state? You lost energy. What happened? How did you lose energy? By doing work. So always remember, when work is done against a resistive force, remember I've introduced the concept of resistive force before. When work is done against a resistive force, that is a pathway for loss of energy. That means work done against a resistive force acts as a path for energy to be lost from a system. So the same way our conclusion should be, as the system is oscillating, this system must be doing work against a resistive force. So as it does the work against a resistive force while it's oscillating, it's also losing energy. So eventually all its energy is lost and it comes to a stop. All right? So damping occurs because work is done. Damping occurs because work is done by an oscillating system against a resistive force. Okay? Now, what's the resistive force here? So this resistive force can be classified into two. Okay? Now, generally, if you take generally, as the system is oscillating up and down, you can see that the system is surrounded in air. So when it goes up and down, the system is opposed by air resistance. So air acts as a resistance. This system must move the air molecules and then push its way through, and then move the air molecules, find its way up, and then move the air molecules, go up, and then move the air molecules, come down, and then it has to keep on doing that. That is what we call air resistance, and by that way, it's losing energy. Now, if we go to more details and all that, now as it oscillates, there will be certain movement over there, and of course, that is not frictionless, it's not a smooth surface. There will be loss of what you call energy there. All right, there will be loss of energy there, but Iwan, for your purpose, we can ignore that. As I said, there are a lot of points we can go into in detail and check and see how the points through which energy is lost, but we are not going to go to that in depth. So we are going to go a little bit general and remain on the surface. So we are only going to take air resistance here. Now, air resistance is seen as an external resistive force. Is seen as an external resistive force. Therefore, loss of energy, that means a large part of energy is lost by this oscillating system doing work against air resistance, which is seen as an external resistance or external resistive force. External resistive force, and therefore this is called external damping. So we classify this as external damping. So what is external damping? External damping is loss of energy by an oscillating system due to an external resistive force such as air resistance, or if you want, you can even say such as frictional force. So frictional force, air resistance are considered as external resistive forces, And that is what we call external damping. If there is external damping, usually there should be internal damping, and let's explore that. So for that, we have to go into more detail. So when this is pushed up, all right, the system will be something like this. The idea is to show that the number of turns are so cramped and the particle is here. Okay? So this is compression. So if you were to see the molecular state, the molecular state here is, this is just a conceptual idea. Yeah? This is the particle that makes up the spring. They are close by purposely making it bigger so you can see for me to explain. All right, that means the interparticle separation distance, I'm creating it bigger. All right, okay, so this is the state. Now when the particle is compressed, this becomes the state. The particles are all of the same size, but their separation distance is closer. So I put it, the separation distance is closer. I'm only putting one linear distance here. Okay, so this is your separation distance I'm taking. I'm putting it this way. Okay, look at the separation distance and look at the separation distance. This is the equilibrium state, original state. So now, remember, in a solid, there are two types of forces between the particles. There are two types of forces between the particles. One, repulsive force. The other one, attractive force. So the attractive force attracts the two particles and bring it closer. But the repulsive force will not allow it to be too close. And when they are too close, it pushes them back. So actually at any time, the particles are actually vibrating at a fixed equilibrium position. And the vibration is due to the interaction of the attractive and the repulsive interparticle force, which is always acting. So actually what is happening, the particle is moving closer, the repulsive forces push back, the particles go up, the attractive forces bring it back, and therefore they are constantly doing this. That is what's happening. So when compression occurs, these particles are pushed closer. So push closer. So in order for these particles to be close, and when the particles are pushed closer, the repulsive force is trying to push them back. But the spring, in order to oscillate, it has to do work against the repulsive force in order to be compressed. The spring wants to be compressed. The spring wants to bring the particles closer. Then only it can get compressed. But to do that, it has to fight against the resistive repulsive force. All right? So there is work done by the particles of the spring. Now, when the spring gets stretched, such as this situation, when the spring gets stretched, okay, here, instead of this, they are far apart. So this time, your attractive forces will try to pull. That means when the spring is undergoing extension, undergoing stretching, which the spring wants, otherwise it cannot oscillate. The spring is pulling the particles apart. But while doing so, it has to fight against the attractive forces which are trying to bring it back. So the spring is doing work against what we call the attractive interparticle force. This is what we cannot see. Why? Because this is microscopic. It's happening inside the system. All right? So what we cannot see, I've already highlighted to you. So as the spring is oscillating up and down, the system is doing work against, in this case, against the repulsive interparticle force during the compression and against the attractive interparticle force during the extension, and hence gradually it's losing energy. And since it is inside the system, which we cannot see, we call it internal damping. Therefore, internal damping is classified into two. Internal damping is classified into two. One, loss of energy due to external resistive forces. All right. Work done against the external resistive forces, that's external damping. 2, loss of energy due to internal resistive forces due to work done against the internal resistive forces, which are namely attractive interparticle force and repulsive interparticle force. That is called, or that constitutes, internal damping.